Um, the work was done by Miss Linh, Thuy, excellent student. She was very disappointed that she cannot come here because her university, Vienna National University, didn't give her funding to travel here. This project is a 4-university collaboration, so I have to make this presentation. It's always risk to present for students because students know every detail and I only know the summary. So this work is interesting because we want to detect the virus in shrimp, which you all love, by detecting the protein specifically. So I will talk in this sequence. I will give an introduction why this virus is important, and I'll talk about how to make the sensor. The sensor is targeted for very cheap material and fabrication, and I will discuss the result. So what is white spot syndrome? And that is a disease shrimp got. At outside shell, you will see this white spot. Under the microscope, they become black. That's because you have to take out the surface. This is actually quite common. In Vietnam in 2021, before Miss Thuy joined the group to develop the sensor, she did a survey. She found out that in one farm, there's a 20% of the shrimp got affected. And whatever shrimp or whenever they got this virus, they will die in 7 to 10 days, and the death rate is 100%, which means that there's a big loss in the profit. So she did a study targeting 2 major shrimp. We all love black tiger shrimp. They are big, juicy, and firm. So this farm, they mainly foster these 2 shrimp, black tiger shrimp and white Pacific shrimp. So she did a study, consider how much time you need, how much feed you need to feed into this farm, and how much it will produce, and how much cost the labor, and what is the potential revenue, because once 20% of the shrimp die, you probably have to clean out the whole pool to clean the virus. And in one crop, the loss is $11 million. And the global shrimp market is 8 to 15 billion, depending on how many different types of shrimp you count. And we estimate is about $1 billion cost from white spot syndrome virus. And this virus is a large DNA virus. It has a rod shape. And on the outside, there's an envelope protein, like we all know COVID protein now outside is S protein. It's the same thing. VP28 is abundant on the surface, so they will dissolve into the water. So you can detect the water to see there's any VP28 protein in the water, and that is a protein folding simulation. So what we want to do is detect this protein. Well, not the first one. There's a group led by Takemura. They studied this using silicon rubber, conductive silicon rubber, and coated with a graphene quantum dot and gold nanoparticle. And as it shows here, that you will start binding to the protein on the virus surface. And when they do so, the impedance change from very small resistance to very large resistance. So we believe that we can use the resistance to detect the protein. And in their demonstration, they show a linear curve that they can show this detection linearly from 10 to the power 2 to 10 to the power 9 DNA copy per milliliter. And their impedance curve also show that the radius become larger and larger. And from the standard deviation, they calculate the limit of detection is 48 copies DNA per milliliter. What they do is that they use the PCR as the verification method. We do not have that luxury to use a PCR, so I will tell you what we did next. So this is our concept. The shrimp shreds protein into the water, and we have a stick that dip into the water, detects the protein, and then put it into a electrochemical impedance measurements and measure the impedance. We use a commercial carbon electrode. The working electrode size is 2.64 millimeters square, and it has a carbon counter electrode and a silver chloride reference electrode. It's a pretty typical low-cost electrode. And then we go into fabrication. We start with the carbon electrode. First, we coat it with CV method with a nanoparticle. I also give, because this video is going online, so I also give the detail of the recipe here. But I don't want to go into detail. The only point I want to point out is that the CV voltage is from minus 0.6 volts to 0.5 volts. And we code it 20 times with 50 millivolts per second scan rate. And then we put this into H2SO4 solution and for CV circle 7 times to try to detect if we successfully grow the nanoparticle on the carbon nanotube, carbon electrode. And then the next step is to grow a self-assembled monolayer of MUA. And that is a layer that can bind the gold nanoparticle to antibody. After we code it, we put it into EDC NHS solution for half hour at 25 degrees Celsius to activate the surface at the top. So they will bind it to antibody. And then this is put into antibody solution for 2 hours at 4 degrees Celsius, and the antibodies start binding to the top. And then we put this into a solution to wash away all the unbound and weakly bounded antibody, so they do not take away the sensitivity or selectivity. And then we wash it in BSA and dry it and keep it at 4 degrees Celsius until we use them. And then when we test them, we use the VP28 protein in different PBS. So this is a control solution and measure them at 4 degrees Celsius. So this is how the whole detection work. So the first is the fabrication. We use a CV curve between minus 0.6 volts and to 0.5 volts. And we repeat 20 times to deposit the gold. We believe that at minus 0.4 volts, the gold was converted on the carbon surface. And then when we do the 7-cycle CV curve, we found a reduction oxidation peak, and that coordinated with the gold particle. And then we also take one new device and tested in SEM, take this photo, and we found the nanoparticle size is about 50 nanometer in diameter. Then we put this into an electrochemical impedance spectrometry. We apply an AC voltage with a magnitude of 10 millivolts, and we scan it from a frequency at from 0.01 hertz to 100 kilohertz. So at the tip here, it was the low frequency, and then the go to high frequency at this end. RS represents the solution resistance. RCT is the charge transfer resistance. So when the antigen binded to antibody, it will generate charge and change the resistance of RCT. And W is the diffusion resistance on the surface, and C is the capacitance of the coating. And we found that at the bare electrode, the impedance is 5.2 kilo ohm. And then when we coated the gold, it dropped down to 0.5. This is also verified that we have the gold nanoparticle coated on the surface. And then we coated with a monolayer and increase start to increase. And then we activate it, we put antibody, and then we wash it. In the end, the curve is the green one. And we started with the RCT about 3 kilo ohm, and that's where we start the measurements. And then we do multi concentration from 0 all the way down to 250 nanograms per milliliter. Remember, what we need to do is that we want to know if this water has that virus or not. So our target is the low concentration to begin with. So in this measurement, we found that the RCT keep increasing linearly, indicating that the impedance measurement can have a linear relationship with the concentration of this protein. We also use a Western blot to test if we can verify if this protein is in that solution. However, we found out at high concentration, the resistance did increase, but did not increase as much as we want. And this will show up in the next slide. And this is a resistance change versus the concentration of the VP28 protein. We found from 0 to 60 nanograms per milliliter, it has a linear relationship with a standard deviation of 31.15 ohm. However, at higher concentration, we believe that the nanoparticle was saturated, so the impedance did not change as much. And using this formula with standard deviation and the sensitivity, we found the limit of detection is 2.38 nanogram per milliliter. So this comes to the conclusion that we successfully deposit a nanoparticle on carbon electrode surface, and we succeeded in functionalization. And then we test in the protein VP28 in a linear range from 0 to 60 nanogram per milliliter. And we calculate the limit of detection at 2.38 nanogram per milliliter. So our conclusion is that this demonstration shows that this could be a good sensing platform to do real-time measurement, especially the electrode can be very cheap, that we can use this to measure a virus. Particularly in this case is try to reduce the price of the shrimp, so we can all enjoy it. So thank you very much.